This is the 5th video in the work and energy topic. In this video we'll be looking at conservative and non-conservative forces. So as a short recap, we've been looking at forces applied to systems, where the system is, for example, the mass on the spring attached to an anchor point or an apple suspended above the ground. And we've been looking at what happens when an external force is applied to the system. And what we've seen is that when a force is applied to the system, and it causes the system configuration to change, so for example the apple moves, then work is done. So in the case of this apple, if we were to apply an external force to lift it up and put it on the table, then we've changed the system configuration, and so we must have done work. And if we are now to return the system to its original state, so say for example by accidentally knocking the apple off the table and back onto the floor, then once again we've changed the system configuration, and so once again work must have been done. So we have two options now. Either the work done in both cases is equal and opposite, so W1 plus W2 equals 0, and in this case the system has been acted on by what we call a conservative force. The other option is obviously that W1 plus W2 is not equal to 0, and in this case a non-conservative force has acted on the system. So we'll look at the definitions of these two forces in a little bit more detail in the next video, but for now we'll just look at two examples of a conservative and non-conservative force. So our first example is gravity. Here we have an apple on the ground, and we do, as we did in the last slide, we apply a force and move it upwards to a height h. So we've done some work on the apple. We know how to calculate this work. We know it's equal to F dot S, so the displacement in the direction that the force was acting, which in this case is equal to mg, our weight force, times h, the height the apple was raised to. I've made upwards positive, so our acceleration due to gravity is negative. Then when we return the system to its original state, we put the apple back on the ground, so we lower it. And calculating the work done in this case is the same, so it's mgh, except in this case both the acceleration due to gravity and the displacement are in the negative direction. So our total work done is equal to 0. So gravity is a conservative force. Our second example is friction. So in this example we'll leave our apple on the ground and we move it a displacement s in the positive direction. We'll calculate the work done as F dot S. So the forces that we have to take into account here, we have our applied force pushing the apple in the positive direction, and we have our friction acting against it. So our applied force is positive and our friction force is negative. So that means our net force is equal to F applied minus the friction force. Since our displacement is positive, that gives us a work as follows. Returning the apple back to its original position by pushing it along the ground, we calculate that work too by the same method. So in this case, friction is acting in the positive direction and the applied force is in the negative direction. Since the displacement is also in the negative direction, we get that our work done in the second case is equal to this. So the sum of W1 plus W2 is in this case non-zero. So the test for path independence is a good test for whether or not a force is conservative. So what we're asking in this case is if the work done on the force depends on the path that the object takes. So does the work depend on the distance or on the displacement of the object? So for gravity, does the work done change if we lift our apple onto the stool or if we push our apple up a frictionless ramp? And in the case of gravity, the force due to gravity is always acting downwards, and so the work is always equal to mgh. So in the case of gravity, the work done depends only on the vertical displacement of our object. So the path doesn't matter. In the case of friction, however, friction is a force which opposes the direction of motion. So if we push our apple in a straight line, friction is always acting in the same direction, and our work depends on the displacement, on the horizontal displacement of our object. However, if we take a different path, so one in which we change the direction that we push the apple, then the direction of friction also changes, since it always opposes the motion. So since the work done is equal to F dot S, in this case, our total work done, we need to sum each of these cases where friction is acting in a different direction. And from that, we see that the work done by friction depends on the path length. So the work done by friction depends on the distance the apple has travelled, rather than the displacement. So for friction, the path taken does matter. So we can say that conservative forces, like gravity, have path independence, and non-conservative forces do not.